motivations of Pdg theory. The motivation for Pdg theory comes from some of the far-reaching goals of the categorification program, which is categorification of the WRT invariant. So the WRT invariant, so it lives in a very special place. A priori, it's a complex number, but it turned out to be some sort of cyclotomic integer for a prime p. So I'll explain this in 1 second. And of course, the WRT invariant is defined at all levels, not just prime numbers, but for categorification reasons, at the moment, we're kind of restricted to prime p. And so this ring bold OP is very closely related to a cyclotomic ring. It's defined to be Z squared Q of the p cyclotomic polynomial evaluated at Q squared. And for a prime p, the p cyclotomic polynomial is a very nice form. It's q to the p minus 1, it's q to the p minus 2, all the way down to 1. And so, so again, this is a slightly different ring than you normally see in homology. But for categorification reasons, that's why we deal with this kind of strange ring rather than just the normal cyclotomic ring. But it's a minor difference. And I also want to say that the fact that the invariant lives in this nice place is it's non-trivial work due to several people, Murakami, Nussbaum Roberts, Lei, Valiakova, Chen, and many others, and it has this very nice integrality property. So one of the goals of the categorification program is to categorify this three manifold. And so the first, maybe one approach to this is to categorify the target of this invariant. So you want to categorify where the three manifold invariant lives. And so that problem was addressed by Habanov more than 10 years ago. We want to categorify OP. So what that, of course, what that means is we want to find a category whose Grothendieck ring is bold OP. Category of VP such that Grothendieck ring is isomorphic. And so we want some nice structure on VP to be a ring. You want it to be a monoidal category. And so this problem was solved by Habanov. So I'm going to take a few minutes now to explain this Pdg theory in this paper about topological algebra. Okay, so we let K be a field of characteristic P throughout the whole talk. And then we have this algebra HT. This truncated polynomial algebra. A joint D mod D to the P, where we take the degree of D to be 2. This is a graded algebra. If you take the degree of D to be 1, which is of course something you could do, then instead of categorifying bold OP, you categorify the normal cyclotomic ring. But this slightly strange grading convention is to match up with other structures in categorification. Okay, so this algebra HP, it's a local graded algebra. So it is a unique simple module up to grade shift in isomorphism. So HP unique simple. So let's fix the simple. So let's let L be the simple one-dimensional module. Concentrated in degree 0. The representation theory of this algebra is very simple. And this immediately tells us a statement about the probability group of this algebra HP. So that tells us that the Grothendieck group of the category of graded modules over HP is isomorphic to the ring of Laurent polymers, where the class of a simple module, and we could shift in the grading the simple module up or down. So my notation for the shift will be this angle. This goes to the monomial Q to the I. Okay. So this is a categorification of the ring of Laurent polynomials, but of course that's not a big deal. The ring of Laurent polynomials can be categorized just by category of graded vector spaces. So we have to do more to categorify this more important ring for low dimensional topology. And so that leads us to the so-called stable category. Sorry, I want to say one more thing before I enter the stable category. The module HP so this is HP is a module over itself, this projective module. It has a filtration with subquotients. So it has a Jordan Holder series, and subquotients are L shifted by 2, L shifted by 4, all the way up to L shifted by 2p minus 2. Okay. And so what that tells us is that in the Grothendieck group, the class of the projective module under this isomorphism, it gets sent to well, 1 plus q squared plus up to q to the 2p minus 2. And notice that's exactly the p cyclotomic polynomial plugging in q squared. And this is precisely the relation that you would want to kill to get the ring Waldo P. So what we would like is we would like for this object HP to be equal to isomorphic to 0. On the category where HP is isomorphic to 0, because then you precisely kill this cyclotomic relation. So that leads us to the stable category. So that HP my underline equal to stable category. So the objects in the stable category are exactly the same as the objects in this normal additive category. Objects name is HP, but we tamper with the morphisms. So in the stable category, between two objects and an end, it's in the stable category. But then we factor out by some subspace. So what is the subspace? The subspace is the subspace of all morphisms from M to N, which factor through a projective. And of course, HP is a projective module, and the identity map, of course, lives in the subspace. So the identity map gets killed in the morphism space of the stable category.
Just to be a little bit more concrete, in this case, projective module are just direct sums of HP. With
exactly. Yeah. In this case, all projective modules are direct sums of shifted copies of HP. Yeah.
Another question, just to be sure, in this, up to now, you don't need characteristic P. Everything you said is valid for K.
Yes. Yeah, so far the characteristic doesn't matter, but in the second, the theorem really does matter. Yeah, so I'm going to write down a theorem where the characteristic really plays a role. So in this category, HP is isomorphic to 0. I'll just kind of make that a note. So we so on the level of the growth in the group, we've effectively killed this relation. And so we get this theorem of Havanov. It says that the growth in the group of this stable category is open. And in order for this to be a monoidal category, you really need to work in characteristic P. So this restriction on the characteristic plays a role immediately now. Okay, so hypothetically, this is where roughly the target of a categorify 3 manifold invariant could live. And so now maybe the task would be to start kind of looking at structures in categorification at generic values of the quantum parameter and try to kind of incorporate this Pdg theory. Any questions so far? Okay. So, of course, the WRT invariant is defined as the sum of color-Jones polynomials at roots of unity, and Jones polynomials or color-Jones polynomials can be defined through the representation theory of quantum SL2. And for a root of unity, one looks at the quantum group at a root of unity. And the quantum group at a root of unity could be viewed as an algebra over bold OP. And so what we want, so this is still kind of some general theory, is we want to be able to categorify modules and algebras over bold OP. Want a procedure categorify modules, algebras over this ring. Okay, and I'll give a concrete example in the next section, but abstractly, this is what we want to do. And so in Pavano's topological paper, he outlines a procedure for this. Okay, so you let A equal be a Pdg algebra. So what that means is that, so first A is a Z-graded algebra. And it comes equipped with a derivation. It's a Z-graded algebra with a degree 2 derivation. So I know 2 and D look similar, but maybe that's good. With a degree 2 derivation, D, such that D to the P is equal to 0. And so if P is equal to 2, this is just a normal notion of a DG algebra. Okay, so this is, a very natural generalization of a DG algebra. And so now I'm going to explain why it's useful to have such a notion. So let's let M be a Pdg module over A. So what that means is that, of course, it's a module over the algebra A, and M itself comes equipped with a map. As an endomorphism, I'll call it D sub M, which is compatible with the derivation in kind of a normal way. has a derivation, has a map d to the m, such that the m to the p is equal to 0 and is compatible with the p differential on A. Compatible. With D. Okay. So we have this category of the Pdg modules over A. And now the point is, and so this category of Pdg modules is going to essentially give us a way of categorifying modules over both OP.
How is it compatible? The compatibility.
Yeah, so it just means that dm of A m is like a dA m plus A. That answers your question? Okay, so let's let M be a module over this algebra that we introduced earlier. Now, a module over this algebra HP, this truncated polynomial algebra. And we again have this module did I just erased the board I wrote? Yes. Okay. Felt like something went wrong. Okay, sorry. Sorry about that. And let me also change notation since I already that was maybe a good thing for me. Okay, so let's let M be a module over HP and N be a Pdg module over A. Then M tensor N over the ground field is a Pdg module over A. Where, so how is it a Pdg module? Well, first, how is it an A module where A acts on the second tensor factor? And D acts by Leibniz rule. So I'm going to use notation with these D's. They're going to look similar. D of M tensor N is dm tensor N plus M tensor dm. And just to kind of clarify, this D is the generator of the algebra HP, and this D is the natural derivation on the module N. Okay, so we now have a procedure where we take an HP module and a Pdg module over A, and we produce a new Pdg module over A. And so that gives us a functor. And I'm going to try not to repeat the same mistake. So we have a functor. In the category of HP modules, that's the category of Pdg modules. Into the category of Pdg modules. So then on the level of the growth in D group, the growth in D group of this is a module over the growth in D group of this. And so we've just kind of reproduced a way of categorifying modules over the growth in D group of this. But the growth in D group of this is just the ring of the Laurent polynomials, which is not the goal. The goal is to categorify modules over the ring bold OP. So we have to do another kind of categorical procedure. And so now I could really erase this. So we have to make another definition. So we define a Pdg mod underline to be the homotopy category of a Pdg mod, and I'll explain what that means. So a morphism F from N1 to N2 in a Pdg mod is said to be no homotopic if there exists a map H from N1 to N2 such that F is equal to a sum from 0 to P minus 1 of d to the I H to P minus 1 minus I. So if P is equal to 2, this just says that F is equal to DH plus HD. That's a normal notion of a no homotopic map of DG modules. Okay. And so the homotopy category is where we kill all no homotopic maps. Okay, and so then Havanov proved that the functor from over here now descends to a functor on the stable category across the homotopy category into the homotopy category. So Havanov proved that we now have a functor from the stable category across the homotopy category into the homotopy category. And so now what that says is that the growth in D group of this homotopy category is a module over this, but the growth in D group of this is the ring bold OP. So K0 of APDG mod underline is a module over bold OP, which is one of the things that we want to set up a procedure to do. We want to categorify modules or algebras over bold OPs. Okay, any questions? All right, one more construction that we need before we see how to start applying this in an example. So it turns out that in some examples which exist, the homotopy category is not enough to categorify quantum groups at roots of unity or representations of quantum groups at roots of unity. And so we need the so-called derived category. So let's let F go from N1 to N2 in the homotopy category. So F is said to be a quasi-isomorphism if, well, so F, of course, it's a map of A modules, it's a map of respecting the Pdg structure. And so what we could do is we could kind of forget the A module structure for a second and just kind of remember that it's also a morphism of Pdg modules, which means that it's a morphism of modules over HP. And so what we could do is we could kind of think about the restriction of F in the stable category of HP. So F is a quasi-isomorphism if restriction of F is an isomorphism in just the stable category. Okay. And so then we let the derived category derived category So we invert all quasi-isomorphisms. And Havana proves that this functor over here descends to now a functor on the level of derived categories. So the growth in the group of the derived category is also a module over both of these. Okay, so I think that ends this background section on PDG theory. I'm going to go back to something a little more classical, but are there any questions?
This was one characteristic P.
Yeah.
Yeah.
I mean, essentially, it's needed to make HD a Hopf algebra, which gives the category more complicated structure. Okay, so now I just want to kind of maybe review or maybe introduce quantum SL2 iterativity. Set up the structures that we're going to actually categorify in this talk. This kind of going to be a zoo of many different quantum groups at roots of unity. So I'll just kind of explain some of them that we addressed today. So I'll let U dot be an algebra over Boldo P. So I'll just say in words in a second. I'll say in words now. This is the Bailenson-Lichtig-McPherson quantum SL2 iterative unity. So it could be viewed as an algebra over OP generated by what would be idempotence 1 sub n divided by power operators L. And these generators get surrounded by idempotence. And divided powers of F. Oh. And plus 2A. And divided powers of F. Subject to kind of some standard relations. So these ones are mutual orthogonal idempotents. These E's multiply in kind of the expected way. And sometimes I'm being sloppy about removing the idempotents. Same thing with the F's. And then there's a mixed relation, E to the A, F to the B, is some, and then you could kind of reverse order. There's some coefficient here. So these kind of look like normal SL2 relations. This is all defined over this this ring called OP. Yeah.
Maybe it gets too technical, but so can you replace relation 3 with just E, the first divided power and the first divided power of, I mean, sort of general things.
Use one E1 and maybe a general.
Yeah, and then use the second one to actually.
Yeah, I believe that. Yeah, that's okay. Probably that's okay, but let me.
Characteristic 0, that would be fine.
Yeah.
Yes, I think this is really sorry. In generality. So this is the so-called big quantum group at a root of unity. And so inside this big quantum group is the so-called small quantum group. Little u, I'll put it out here. Be the subalgebra generated by these idempotents, and then just the first divided powers. This is still an infinite dimensional algebra because of these mutual orthogonal idempotents, but its category of representations is equivalent to category of representations of some finite dimensional algebra. That's why it's called small quantum group. Okay, and inside the small quantum group is kind of the positive half. So as quantum SL2 for generic values of Q, the positive half is just the polynomial algebra in the generator E. And so little u plus at a root of unity is kind of a truncation of that. Oops. In some sense, we now have a kind of containment of algebras. U plus, since inside of little u dot, which is since inside of big U dot. So this is the big quantum group, small quantum group, and this is the positive half of the small quantum group. Okay. And so we want to be able to categorify some representations. Well, we'd like to categorize as many representations over these algebras as possible. So I'll just kind of quickly say the representations that we consider. So let's let L be the vial module over U dot. So this is an L plus 1 dimensional module. So its basis V0 through VL, and E's and F's, they act kind of in a standard lowering and raising sort of way. So this, for generic values of Q, this vial module is irreducible, but at a root of unity, these things are no longer irreducible. And of course, we could take tensor products of these modules. So we'll want to categorify. At the moment, we can categorify tensor products of the two-dimensional vial module, arbitrary tensor products, and a tensor product of two vial modules. So, of course, you would want to categorify arbitrary tensor products of these vial modules and even more sophisticated representations, but we don't have techniques to do that at the moment. Okay, so that's just a kind of quick review of quantum SL2 at a root of unity, and now I'll give concrete examples of some Pdg algebras. So this will be categorification of these kind of quantum groups.
So you assume this L to be smaller than P?
I'm sorry. So these vial modules exist even if L is bigger than or equal to P. If L is less than or equal to P minus 1, it's irreducible. But we can categorify L be the vial modules even when they're not irreducible. So now I'm going to introduce the Nilheka algebra. So this is the Nilheka algebra over our field of characteristic. So I think most of you probably have seen this, but I'll just kind of quickly say. So it's generated by polynomial generators yi, and there's a graphical interpretation. So yi has a graphical interpretation in terms of these kind of diagrams, with decorated diagrams. So we put a dot on the ith strand. Psi I where we have a crossing between the I and I plus 4 strands, modulo some relations, which maybe I won't write down. So this is a Z-graded algebra where this has degree 2, and this has degree -2. And it's this grading convention which kind of forced us into taking this weird grading on HB earlier. Okay, modulo some relation, subject to some relation. And so it's well known that this nil-Hecke algebra is an example of a KLR algebra. KLR algebras categorify upper halves of quantum groups for generic values of Q. And so what we would like to do is we'd like to endow this nil-Hecke algebra with a Pdg structure. So NHN has a Pdg structure. So I define it on the generators. D of yi is yi squared. D of a crossing, easier for me if I draw it graphically. It's minus, we put a dot up here, minus a dot down here. Okay, and this is a degree 2 endomorphism, and then it's a fairly easy check to see that d to the p is equal to 0. And then you extend by linearity and Leibniz rule to the entire nil-Hecke algebra. And so then a theorem of Pavan and Vinci says the following. So again, for generic values of the quantum parameter, what you normally do is you take categories of modules over nil-Hecke algebra or KLR algebra. You look at their Grothendieck group, you look at a tower of algebras. And so we look at kind of the analog here. So if we look at the direct sum over all n of the derived category of NHN with respect to this P differential, and if we look at the Grothendieck group of this is isomorphic to U plus. This was the positive half of the quantum group at a root of unity. And so this is an isomorphism of Lie algebras. And so there's a couple of interesting features of this. Probably the most striking thing is that the left-hand side a priori looks infinite dimensional. The right-hand side is a finite dimensional algebra. So a lot of work needs to be proved to show that these categories actually collapse if n is bigger or equal to p. And of course, if n is less than or equal to p minus 1, it has to be one-dimensional. Okay, so this was a theorem which signaled that this Pdg theory is really useful in categorifying structures at roots of unity. And then I should just kind of mention that this theorem was then extended to a categorification of the full small quantum group and the full and the big quantum group. So the theorem of Linus and she says that the Grothendieck group, so I'm not going to define this, but there's the Lauda SL2 category, which is kind of a doubling of the nil-Hecke algebras. So the Grothendieck group of the derived category of the Lauda SL2 category is isomorphic to the small quantum group, and growth in D group of, so this is the Lauda SL2 category. And the derived category of the so-called Karoubi envelope of the Lauda SL2 category is isomorphic to this whole quantum group. So this is the Karoubi envelope. So in the last few minutes, I'll talk about now categorifications of the representations. Okay, yeah. So right. So the question. Yeah, exactly. For E, it's the same. So for the crossings, it's the same. So essentially, you have to define it for cups and caps. And well, there's an explicit definition, but
Okay, and it's kind of complicated.
it's a little complicated, yeah. I mean, by degree considerations, there aren't too many things it could be, but then you just have to kind of set up what the coefficients of it are and just check that.
So all the bubbles appears.
Yeah, bubbles appear and some extra dots appear. Yeah. Okay, so now in this very last section, I'll talk about categorification of representations. So first we let NH and L be the so-called cyclotomic Nilhecke algebra. So this is the Nilhecke algebra, but then we kill the L's power of this first polynomial generator. Okay. And it's fairly easy to see that this is a Pdg algebra. This ideal is preserved by the P differential. And of course, for generic values of Q, it's known that cyclotomic Nilhecke algebras and more generally cyclotomic KLR algebras categorify irreducible representations at generic values of the quantum parameter. But now we have a theorem of Ysng. This is now in the context of the P differential over a field of characteristic P. So this says that if we look at, first we look at a direct sum, n goes from 0 to L of the derived category of the cyclotomic algebras. If we look at their growth in D group, this is isomorphic to VL, assuming L is less than or equal to P minus 1. These cyclotomic Nilhecke algebras categorify the irreducible Weyl modules. Not all Weyl modules, just the irreducible ones. And so now the kind of the last algebraic construction, which is maybe less familiar, unfortunately I'm running a little bit out of time, is to look at certain modules over cyclotomic Nilhecke algebras. I'm sorry? Okay, okay. So I want to introduce certain modules over cyclotomic Nilhecke algebra introduced by Hu and Mathis. So I just need a little bit of combinatorial input. Okay, so this is not a good piece of chocolate. So I'm going to let P and L. This is some sort of combinatorial set. So this is L tuple of zeros and ones with n ones and L minus n zeros. So there's L minus n zeros and n ones. Okay. And now if we take then to an element of sequence of zeros and ones, we associate a monomial. Say y lambda. So it's the following monomial. It's y1 to the L minus a1 dot 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 yn to the L minus an, where these ai's signify where the ones occur. AI is the position of the ith. Okay, so these exponents are strictly decreasing. Okay, and so we have this these elements, and now I define these homomorphism modules. So now I let G lambda, the right module generated by Y lambda, and it's easy to check that this is a Pdg module. And so now finally, I could define the so-called Pdg Quebecer algebra. So we let SNL be the endomorphism algebra over NHNL of the direct sum of all these G lambdas. So this is called the Pdg Quebecer algebra. This was studied in much greater generality by homomorphisms for other types of KLR algebras. But for us, for SL2 categorification, we're just interested in this kind of special case. Okay, and this naturally, well, these G lambdas are Pdg modules. This endomorphism algebra then naturally comes with a P differential. So SNL is a Pdg algebra. And so now finally, state of theorem. So in joint work with Chi, we show that if we look at the derived category of these SNLs with its natural P differential, we take a sum that goes from 0 to L, and we get the growth of the group of this. And naturally, we have this categorification of U1 tensor L, and this isomorphism is an isomorphism of U dot modules. Isomorphism of modules over this big quantum group at a root of unity. Okay, and I am really running out of time, so I'll just say kind of briefly, using a modification of these Quebecer algebras, we can also categorify a tensor product of two general viable modules. And there are candidate algebras to categorify a more general tensor product, but proving things about the growth in the group is a little technically complicated and beyond our reach right now. And hopefully this could be extended to categorification of link invariants. And hopefully at some point WRT invariants. And I think that maybe this is a good place to stop. Thank you.
Okay, so questions for Josh? Ask a question. So in your paper with which you have several versions of the Quiver-Schur algebra, right?
Yes. So I should say that this Quiver-Schur algebra, it comes up in various contexts in representation theory. So it's Morita equivalent to Webster's diagrammatic algebra. It's smaller than it, and we prove that it's Pdg Morita equivalent. Webster proved without the P differential that these Quiver-Schur algebras are Morita equivalent. They're equivalent by various chains of equivalences to singular category O. And then I don't know if this addresses your exact question, but also to categorify general tensor products, we need some sort of kind of modification of these Quiver-Schur algebras, which depends on some slightly different combinatorial data in this KL.
And this is connected to the geometry of quiver varieties construction by Webster and Stropel?
Yeah. So I should say that as well, is that although I can't say precisely what the connection is that there's a geometric construction via convolution of by some convolution algebra connected to geometry. So they have a geometric construction of this.
Might be interesting to see the P differential in the geometric context.
Yeah, I agree. Yeah, this is looking for P differentials in purely Lie theoretic context or purely geometric context is kind of an open question.
You think about categorification of left tensor product with categorification of V1 in the sense that it could be a functor about the functoriality of this process of tensor on the left.
Oh,
because that would be important for the stabilization.
So I see. So maybe are you just to maybe reformulate? So you're asking about a categorical way of kind of
Yes.
Like in the Rouquier sort of. Yeah, that I don't. Yeah, that I don't know. I think that's a good question. I think it's very complicated. And I mean, in this kind of Webster's type style, just kind of categorify this, but the notion of kind of categorification of tensor into representations is work of kind of Rouquier and Magnin, but that's
the question is in which sense this is it natural?
Right. Yeah. Exactly. Yeah. So it's a good question. I don't answer to that.
Okay, so let's thank Josh once again.
Thank you.